Hey everyone! Welcome back to physics, where electrons don't just move, they dance to our commands. Now, before your sleek smartphone chips came into play, imagine a time when computers filled entire rooms and literally glowed like old radio sets. Back then, we controlled electricity using big glass tubes called vacuum tubes, or as engineers fondly called them, valves. Why valves? Because, just like a water tap, they allowed current to flow only in one direction, from cathode to anode. Inside that glass bulb, a heated cathode would throw out electrons, a bit like popcorn jumping in hot oil, and the anode would collect them. But there was a catch. You had to maintain a vacuum inside. If even a bit of air sneaked in, the electrons would collide and lose energy, ruining the show. The result? Devices that were bulky, power-hungry, and needed almost 100 volts to do simple switching. Think of using a truck engine just to power your calculator. Still, these vacuum tubes were heroes of their time. They made early radios and the first computers possible. Fast forward to the 1930s, the age of discovery. Scientists realized something revolutionary. We could control the flow of electrons inside certain solids like silicon and germanium without needing a vacuum or heat. These were called semiconductors, tiny crystals that could change their conductivity when exposed to light, heat, or a small voltage. It's like finding out you could control traffic just by shining a flashlight instead of building roads and traffic lights. And then, the world changed forever in 1948 with the invention of the transistor, the little genius that replaced bulky vacuum tubes. Suddenly, circuits became smaller, cooler, and far more reliable. These devices didn't need heaters, glass shells, or high voltages, just clever materials and quantum physics. That's when electronics officially entered the solid-state era, the foundation of everything from computers to mobile phones. Now, here's a fun fact. Before transistors, people were already using semiconductors, even without knowing the fancy science behind them. Meet the galena crystal detector, a chunk of lead sulfide with a thin metal wire touching it. This setup, called a cat's whisker detector, could pick up radio waves. You tune your crystal like an old-school physicist, moving the wire until you found that sweet spot where signals suddenly played through your headphones. This was one of the first practical uses of semiconductors, a small step that later inspired the mighty diode and transistor. So, from galena detectors to silicon chips, it's been quite an electrifying journey, literally. Let's now draw a quick comparison between our old friends, the vacuum tubes, and the new kids on the block, semiconductors. Vacuum tubes were like vintage cars, classy, powerful, but high maintenance. They worked at 100 volts, needed heaters, and guzzled electricity like crazy. Semiconductors, on the other hand, are the electric scooters of physics, tiny, eco-friendly, and running at just 10 volts or less. If you've seen old CRT televisions with those deep backs, that's vacuum tube technology. Now, compare that to your flat LCD or LED screen. That's all thanks to semiconductors. And the best part? You can now fit billions of transistors inside something smaller than your fingernail. That's Moore's law in motion. As for power, remember the formula P equals V times I, lower voltage and lower current? Way less power consumed, way more efficiency. Alright, let's peek inside a semiconductor crystal, where the real magic happens. Inside, we have electrons that can move freely when energy is supplied, and holes that act as positive charge carriers. Think of it like a dance floor. When one electron moves away, it leaves behind a hole, and another electron moves in to fill it. Together, they make a chain of movement, that's current. In vacuum tubes, electrons move through empty space, like people jumping from one rooftop to another. But in semiconductors, they move within the material, faster, smoother, and with far less energy loss. That's what makes semiconductors not just smaller, but smarter. They allow us to precisely control current without waste. This is the reason your phone doesn't need fans or vacuum bulbs. Everything's happening quietly inside the solid crystal. Let's do a quick number crunch to see just how efficient semiconductors are. Suppose we've got a vacuum tube running at 100 volts and drawing 0.1 ampere. Using our trusty formula, power equals voltage times current, we get P equals 100 times 0.1 equals 10 watts. Now, take a semiconductor doing the same job but at 10 volts and 0.01 ampere. That's P equals 10 times 0.01 equals 0.1 watt. So, the power used is 100th. Imagine running your laptop on the energy needed to light a single lid. That's why semiconductors revolutionized electronics. They're efficient, cool, and long-lasting. No wonder your smartphone battery lasts hours instead of minutes. So to wrap this up, we started with the clunky vacuum tubes that needed heat, high voltage, and a lot of patience. Then came the elegant era of semiconductors, tiny solids where electrons and holes do the work inside the material itself. The invention of the transistor in 1948 changed everything, leading to diodes, integrated circuits, microchips, and the modern digital age. Every computer, every gadget, every smart appliance all trace their ancestry to this moment in physics history. So next time you hold your phone, remember, you're literally holding the evolution of 100 years of electron control packed into a few grams of silicon magic. That's the beauty of physics, turning glass bulbs into galaxies of circuits. See you in the next session where we dive even deeper into how these semiconductors work inside, starting with junction diodes. Stay curious, stay charged.